Well, previously we looked at carbon dioxide and we looked at the power of hydrogen. This time we're going to look at ions and ionization and the concept of the ion dissociation constant, the pKa. The ripple of ions. This tutorial, which is tutorial 3 of the acid-base course, is on ions and the ion dissociation constant, or pKa. I want to warn you in advance, this tutorial is quite sciencey, but it's not nerdy. And if you really want to understand particularly metabolic acid-base chemistry, you really need to know what I'm talking about in this tutorial. Previously, I discussed carbon dioxide production and chemistry and why carbon dioxide is the most important acid in the body. I explained what happens in apnea, what happens in acute respiratory acidosis or acute hypercarbic respiratory failure, what happens with acute respiratory alkalosis where patients hyperventilate. And I also discussed patients who have COPD, who chronically hypoventilate and have high levels of bicarbonate and low levels of chloride in their blood. This time I will explain the concept of charge or valency, dissociation equilibria and the pKa or ion dissociation constant, and I will introduce a term known as strong ions. So far in this course, we have seen that all acid-base reactions occur in the aqueous medium, that is, body fluids, and that carbon dioxide is the major acid in the human body. Changes in the partial pressure of carbon dioxide in the blood cause respiratory acidosis if the pCO2 goes up, and respiratory alkalosis if the pCO2 goes down. There is an entire other spectrum of disease that affects acid base. And these are diseases like diabetes, acute kidney injury, sepsis, trauma, and even fluid resuscitation. And what they do is they generate compounds that dissociate and then have an impact on hydrogen to hydroxyl balance in the body. And these are known as metabolic acidoses and metabolic alkaloses. Key to understand the metabolic component of acid base is that you need to understand what charge is. I'm going to start with a very common ion in the body, sodium. And you know sodium is Na+. It carries a positive charge. It is an ion. Now normally in nature, sodium doesn't exist as Na+. It exists as a salt where it's bound up with a second agent that carries a negative charge, such as chloride, and we call that table salt, NaCl. But when we measure sodium in chemistry and in the body, we measure the quantity of sodium usually as millimoles. For example, the normal plasma sodium is 140 millimoles per liter. The osmotic effect of a single particle of sodium is measured as milliosmoles. The way we measure the charge is known as valency, and because sodium has a single charge on it, the valency measured in milliequivalents per liter is counted in the same way as the quantity in millimoles. So if sodium has a quantity of 140 millimoles per liter, it has a valency of 140 milliequivalents per liter. In this case, 1 millimole equals 1 milliequivalent equals 1 milliosmole. And the same is true for potassium, chloride, bicarbonate, lactate, keto acids, etc. Calcium and magnesium, which are Ca2+, and magnesium, Mg2+, are divalent. That means for every 1 millimole and 1 milliosmole, there are 2 milliequivalents. So what you have is one particle, 2 charges. And that's important because those 2 charges must be accounted for in electrical neutrality. Throughout this course, we're going to refer to chemical charge or valency in milliequivalents per liter. Now imagine the body as a big bag of water. In that water, we're going to dissolve some stuff. For example, we're going to dissolve carbon dioxide and bicarbonate. These both have chemical activity that impact water dissociation. We're also going to dissolve some mineral and organic salts, and they're going to break down into their component parts in water. There's other stuff in there that's floating around like urea and glucose that are chemically neutral. They just bop around the water and have no impact on water dissociation because they do not ionize. Mineral and organic salts ionize into their component parts. It's essential to understand that the supply of hydrogen ions in that water is unlimited. One of the major rules and laws of the universe is that electrical neutrality must always hold. All of the positive charges must equal all of the negative charges. And there are only a limited number of charged particles in the body, and some of them cannot be created or destroyed, and that is known as the law of mass conservation. In this particular illustration, I've put a load of things into a container of water. Take the white items, the golf balls, as being positively charged and the green tennis balls as being negatively charged. If you come along and you increase the amount of fluid, the amount of water around these particles, the quantity does not change, just the dilution. So for example, if you overhydrate a patient, their plasma sodium and chloride and potassium will drop. The total amount of sodium is the same, but the dilution causes the concentration to fall. Likewise, if you remove liquid from this system, the quantity does not change, just the concentration. So if somebody becomes profoundly dehydrated, their sodium, potassium, and chloride levels go up, but the total quantity of those electrolytes remains the same in the body. Likewise, carbon dioxide exists independently of the majority of these particles. The number of particles does not change. Key thing to understand is that ionic particles are charged. An acid-base balance is all about charge distribution. Now, water carries charges. Remember, it can dissociate into its component parts, hydrogen ions, hydroxyl ions attached to clumps of water. But the hydrogen ion supply is unlimited and the amount of hydrogen ions is minuscule. And we've talked about this in the first tutorial. The intracellular pH is chemically neutral with respect to water at 37 degrees, and the hydrogen ion activity is 100 nanoequivalents per liter. The extracellular pH is 7.4, which makes it slightly alkaline with respect to water, and the extracellular hydrogen ion activity is 40 nanoequivalents per liter. So what carries charge, positive or negative, in the human body? The first thing is carbon dioxide. Carbon dioxide is hydrated to carbonic acid, and that of course is cleaved to bicarbonate and a clump of water with some hydrogen sticking out. That binds up to hemoglobin in the erythrocyte that buffers the effect of carbon dioxide on venous blood. Now, the carbon dioxide bicarbonate supply is actually limited despite the body manufacturing it, because the body tries to lock the PCO2 to 40 millimeters of mercury or 5.1 kPa and the bicarbonate to around 24 milliequivalents per liter. And they stay there. When you start to exercise and you start to ventilate more, what the body's trying to do is get that CO2 to where it belongs, 40, 5.1 and 24 milliequivalents per liter. It's only when patients hypoventilate that the bicarbonate level rises and the CO2 level rises. The other thing that can affect the charge across water in the body are mineral salts. And generally a salt is a positive charge attached to a negative charge. So the positive side might be sodium, potassium, magnesium, or calcium, and the negative side may be chloride or phosphorus. So when you a table salt, what you're getting is sodium and chloride stuck together. If you dissolve that salt into water, it splits into its component parts, sodium and chloride. It could be potassium chloride. It doesn't matter. Once that salt is put into water, it breaks down into its ionic particles. The supply of all mineral salts in the body is limited, and it's determined by mass conservation, and the body goes to a lot of trouble to keep the levels of those salts very, very tightly calibrated. For example, the plasma sodium is 140 millimoles or milliequivalents per liter, and it stays around that level. The body will ingest sodium and it will excrete sodium, and it will try to do that to keep sodium at the same level. If a patient becomes overhydrated, the sodium drops. If they become dehydrated, the sodium rises. If the patient becomes dehydrated, they get very thirsty. They want to drink water to bring the sodium down. Organic salts are manufactured by the body. These include lactate, ketones, citrate, fumate, sulfate, or metabolic junk products that sometimes are referred to as renal acids. If you were to collect these out of the blood, they would turn into salts bound to something else. For example, sodium lactate. But biologically, they all exist independently as negatively charged particles. The quantity of all organic salts is limited and determined by production and elimination. And the production is continuous for all of these different negatively charged compounds. But the elimination is just as fast. So if the liver is working and the kidneys are working, you can't really measure ketones or lactate in the blood because the stuff is being processed so fast by the body. When the body becomes diseased, suddenly the level of these anionic compounds increases, and that manifests as metabolic acidosis. When you dissolve salt in water, the compound breaks apart. And what determines how much the compound breaks apart is a thing called the ion dissociation constant, or the pKa. Remembering that the pH of extracellular fluid is 7.4. The further the pKa is from that 7.4, either downwards or upwards, the more likely, depending on whether it's an acid or a base, the compound is dissociated. In this situation, the pKa is 3.5, so this is a strong biological acid, and at that level, every single particle is fully dissociated. There are no associated particles. And this is typical of, say, for example, lactic acid. There are no particles of lactic acid in the body. It is fully dissociated across the entire range of potential pHs that we can have and still be alive. So it exists only as anionic lactate. You may be surprised also to hear that chloride is functionally the same thing. Hydrochloric acid is fully dissociated at all physiologic levels of pH. When we talk about these fully dissociated particles, because they cannot be associated into salts in living beings, we call them strong ions. Sodium is a strong cation. It never exists in the body bound to anything. Chloride is a strong cation. It never exists in the body bound to anything. When you think about chloride, you need to think that it represents hydrochloric acid. When you think about sodium, you need to think that it represents sodium hydroxide. Not all acids and bases are fully dissociated. If the pKa is close to the range of physiologic pH, in this case it's 6.1, we call this a weak acid. It's a weak acid because the pKa is below 7. It's a weak base if it's higher than that. In this situation, not all of the acid is dissociated. So what you have here is partially dissociated acid. This is important because these particular acids are capable of acting as buffers. When the pH falls, they become more associated, so they pick up hydrogen ions and act as buffers. These weak acids include bicarbonate, albumin, and hemoglobin. So ionic particles are either completely or incompletely dissociated. Completely dissociated ionic particles are strong ions. I now want to explain the pKa a little bit more. This is the ion dissociation constant, and it is defined as the pH at which the acid or the base is 50% dissociated. For an acid, the further the pKa is below the pH, the more associated the acid. So it's more A minus plus H on this end. The further the pH is above the pKa, the more dissociated the acid. I'm going to give you an example. Let's look at lactic acid or lactate. Lactic acid has a pKa of 3.5. That means at this point it is 50% dissociated and 50% associated. So 50% of this compound at a pH of 3.5 is lactic acid and 50% is lactate. Were one to take the pH down below that level, there will be more lactic acid than lactate. If you go above that level, there's more lactate than lactic acid. As you go above a pH of 6.5, this compound is fully dissociated. Consequently, at all physiologic pH levels above this, that is the range of life, there are no lactic acid particles present. So in the human body, there are no lactic acid particles. It is all anionic lactate. It's always fully dissociated at all physiologic pH levels. So functionally, it acts as a strong acid in our body. Conversely, carbonic acid stroke bicarbonate has a pKa of 6.1. Although that is a fair distance from 7.4, it is still partially associated at all pH levels associated with life. Indeed, the degree of dissociation decreases as the pH falls. That makes it a very effective buffer. So bicarbonate is partially dissociated at all physiologic pH levels. Alkali associate in the opposite direction. They're the opposite of acids. They are fully associated at higher pH levels and highly dissociated at lower pH levels. For example, sodium hydroxide has a pKa of 15.7. That makes it a strong physiological base. There is no sodium hydroxide in the body, only the strong ion sodium. This table displays the pKa's of common mineral and organic acids and bases in the body. The first one, hydrochloric acid, has a pKa of less than 1. It is a strong physiological acid. It's fully dissociated, and when you see this in the body, it's known as chloride. Acetoacetic acid has a pKa of 3.58. It is a strong physiological acid, and in the body it's known as acetoacetate. Lactic acid has a pKa of 3.8, is a strong physiologic acid, and when we see it in the body it's known as lactate. Beta hydroxybutyrate has a pKa of 4.41, which means that it's fully dissociated at all physiological pH levels. In the body, we know it as beta hydroxybutyrate. This is a ketone, as is acetoacetate. Carbonic acid has a pKa of 6.1. That makes it a weak physiological acid. It is partially dissociated, and the dissociated component is known as bicarbonate. Sodium hydroxide has a pKa of 15.7. That makes it a strong physiologic base, and because bases are the opposite direction from acids, it is fully dissociated at physiologic pH, and therefore it exists only as a sodium ion. Potassium hydroxide has a pKa of greater than 12, and it's a strong physiologic base, and we know it physiologically as potassium. So this may appear a little bit stupid, but the human or mammalian body is a finely tuned, fragile ecosystem. And what is considered a weak acid by a chemist, for example, lactic acid, is actually a strong acid in a biological system. The body is not a test tube, but a highly complex system. So chemistry terms like conjugate base are irrelevant in physiology. And that's why it's important to understand these strong and weak acids. Here I have the range of pH in life, which goes from about 6.8 to 7.6, something like that. And I have 7.4 in the middle. Hydrochloric acid, citric acid, lactic acid, and various keto acids, because their pKa's are down below 4, they are physiologically always fully dissociated, and we see these as dissociated anions in our clinical practice. Likewise, sodium, potassium, magnesium, and calcium as hydroxides have pKas in the range of 12, 13 or higher. They are always dissociated physiologically in our bodies, and we see them only as cationic ions. Albumin, carbon dioxide, bicarbonate, carbonic acid, and phosphoric acid are all weak acids, and they exist partially associated and partially dissociated in physiology, and they function as buffers, as does hemoglobin. So strong acids and bases are completely dissociated. Weak acids or bases are incompletely dissociated. Now I want to move on and talk a little bit more about strong ions. To me, strong ions are like dodgy prom dates. A couple may go into the prom, but as soon as they go in the door, phoomp, they separate and never see each other again. And in this situation, we have a cation and an anion bound to one another going in the door. But as soon as they go in, and the analogy of this is as soon as that salt is dissolved in water, they separate, they ionize, they entirely separate out into their component parts. Now, for every one of those cations, there must be a hydroxide, and for every one of those anions, there must be a hydrogen ion, or a blob of water containing one or the other. Strong ions are ions that are always unbound due to a high or a low pKa. So in our bodies, we have both strong cations and strong anions. The cations are sodium, 140 milliequivalents per liter, potassium about 4 milliequivalents per liter, magnesium 1 to 2 milliequivalents per liter, and calcium 1 milliequivalent per liter, to a total charge of 146 milliequivalents per liter. The law of electrical neutrality must always hold, so all that positive charge must be balanced by negative charge. And the negative charges are chloride, 105 milliequivalents per liter, lactate, less than 1, ketones, less than 1, renal junk anions, less than 1. And so the strong anion content is only about 106 milliequivalents per liter. So there's a gap there, where there's a distance between the strong cations and the strong anions. 146 versus 106. So we have 40 milliequivalents of missing anion if we just count up the strong anions and strong cations. And this is known as the strong ion difference. What makes up that charge, that difference between the strong cations and the strong anions, are the charges carried by weak acids, principally albumin, bicarbonate, and phosphate. Sometimes I think of acid-base balance as being a tug of war between the cations and the anions. And the cations have a slight unfair advantage, hence the pH is at 7.4, not 7. So I've set the mid-zone here at 7.4 and with a strong ion difference of 40 milliequivalents per liter. To the left, the pH falls towards 7, and to the right, the pH rises to 7.6. The cations are on the right-hand side, and the anions are on the left. 2/3 of the difference in charge between the cations and the anions is made up of bicarbonate, usually at 24 milliequivalents per liter. Now, most of the nasty stuff that causes problems with acid-base chemistry is on the anionic side. So we're going to add in some strong anions, in this case, beta-hydroxybutyrate. The distribution of hydrogen and hydroxyl changes to favor hydrogen. The hydrogen ion activity increases due to a fall in the strong ion difference, and the pH falls. However, immediately the surplus hydrogen ions are mopped up by bicarbonate to form carbon dioxide, and the pH returns towards 7.4. Now, if the patient is unable to blow off the additional carbon dioxide, if they're on a fixed minute ventilation, for example, on a ventilator, then the pH remains low. So core to understanding acid-base is that when anions are additionally added into the system, like beta-hydroxybutyrate or lactate, there is a 1 milliequivalent per liter fall in the bicarbonate for every 1 milliequivalent per liter gain in anions. This is true whether they are easily measured like chloride or sometimes unmeasured like keto acids. To summarize the concept of the strong ion difference, let's look at this picture. And what we have is the relative ratio of hydrogen to hydroxyl. As the strong ion difference reduces, the ratio of hydrogen to hydroxyl increases, and that leads to acidosis. As the strong ion difference increases, the ratio of hydroxyl to hydrogen increases, and that results in alkalosis. There is nothing new about strong ion difference. You may not be familiar with SID as a concept, although the term originates in the 1970s. It is part of a continuum that goes all the way back to Henderson in the 1920s. Sometimes it's been known as buffer base or alkali reserve, or even the anion gap in some terminology. But it's been around a long time. And if you look at the schools of thought of acid-base chemistry, it is part of the electrochemical school that was the prevalent school up to 1955, and in some quarters is the prevalent school today. The alternative school, as I mentioned in the tutorial on carbon dioxide, comes from both Boston and Copenhagen, and I will go through these in detail in a future tutorial. They really emerged in 1955, and they've been the dominant school amongst medical students and residents and attendings in medicine for many decades. And if you really want to know the difference between the two, essentially the Boston and Copenhagen schools focus on the base deficit or the base excess, or the relationship between the PaCO2 and the bicarbonate. And the electrochemical school is very much based on the difference between the strong anions and the strong cations. So the anion gap, the strong ion gap, or the base deficit gap will be examples of techniques you may use if you're a member of the electrochemical school. The electrochemical school believes in measuring everything, and they believe that this adds to the precision, but also to the complexity of diagnosis. This is the approach to take if you have a critically ill patient with multiple acid-base chemistry abnormalities going on simultaneously. The Boston and Copenhagen schools, they call themselves the traditional schools, but they are actually neo-traditional schools. They limit measurements and they rely on simple rules of thumb, and this leads to rapid assessment, but there's very low precision. So for a patient who rolls into the ED with a single problem, these rules work very well. When they've been in the ICU for 5 days and multiple things going on, the level of precision falls off a cliff. As a consequence, for many of us intensive care specialists, we have moved very much back to the electrochemical school, and a lot of the modern thinking about acid base is built on the work of a Canadian physiologist, Peter Stewart, from the late 1970s and 1980s. And I will go into detail later in this course about what we learned from Peter Stewart, who originated the term strong ion difference. All of this is fully consistent with previous understanding of acid base, but it fills in a lot of the gaps and it explains a lot of the stuff that was previously unexplained. In the meantime, let's review this tutorial. This was a tutorial about ions. Ions carry electrical charge characterized by valency in milliequivalents per liter. Electrical neutrality must hold across all body systems. The degree of dissociation of acids and bases is determined by the pKa, the ion dissociation constant. Strong ions are always fully dissociated. Examples of these are sodium, chloride, potassium, calcium, magnesium. The difference in charge carried by strong cations and anions is the strong ion difference, and it's always positive, and the electrical balance is provided by weak acids, bicarbonate, albumin, and phosphorus. Derived from this concept is the anion gap, the strong ion gap, and the base deficit gap, and I will explore those in later tutorials. The next time I will discuss the concepts behind metabolic acidosis, what buffers are and how we compensate, and an introduction to the systems for interpreting metabolic acid-base balance. I'll see you then, and I guarantee you'll learn something. So that was ions and the pKa. I hope you found it useful. Don't forget to subscribe on YouTube, leave me some comments and some likes, or follow me at ccmtutorials.org. Next time we're going to tackle the problem of metabolic acidosis.